Hello, and welcome to our presentation for our 2026 Capstone 2 project, Math Unikernel. My name is Lucas, and joining me are my team members Eddie, Ian, Julian, and Lewis.
To understand the motivation behind why we built the Math Unikernel, we first have to look at the limitations of standard operating systems. In short, traditional operating systems are simply too loud, meaning they introduce what we call system noise, which is unpredictable jitter caused by background tasks, hardware interrupts, and complex CPU schedulers, constantly juggling priorities. For everyday computing, this isn't a problem, but for hardware-accelerated mathematical workloads, it creates a massive bottleneck. This is because background noise steals critical CPU cycles and entirely destroys execution determinism. Because the operating system is constantly interrupting the workload to handle other tasks, it becomes impossible to guarantee exact execution times for precision mathematical operations. Our goal was to eliminate this interference, which is why we set out to build a specialized 64-bit bare metal operating system that provides a completely deterministic single address space environment. That brings us to our solution. We custom built exactly that, a specialized 64-bit bare metal environment. By stripping away the standard OS layers, we created a highly deterministic single address space architecture where our mathematical workloads have total uninterrupted control of the system. To achieve this efficiently, we utilize the Lamine boot protocol. This allows us to completely bypass legacy BIOS and UEFI startup overhead and boot instantly into the 64-bit long mode. Finally, we didn't want this to just be a theoretical backend. To make this unikernel accessible and practical for use, we also built a custom VS Code extension. This allows users to seamlessly write, compile, and execute their workloads directly on our bare metal environment right from their editor. Now I'll pass it on to Ian to begin explaining the first component of our environment.
So this diagram showcases the boot sequence as a three-stage handoff between the bootloader, our assembly stub, and the kernel core. So Lamine is responsible for handling the first phase by negotiating the protocol and then validating all the different hardware preconditions, before then passing the memory map and hardware state across to the assembly stub. Then the assembly stub is responsible for getting the CPU into a clean state before any of the C code can actually run, by setting up the stack, aligning it to the system VABI so that the function calls behave correctly, and then terminating the call frame so that stack traces have a defined boundary and they don't end up walking into garbage memory. Then once all that is completed, the control transfers to the kernel core and we can begin the initialization sequence by bringing up each hardware subsystem one by one until the kernel is finally ready for receiving work.
This diagram outlines the core kernel components of our 64-bit bare metal architecture. By utilizing the Lamine boot protocol mentioned earlier, we bypass legacy startup steps and boot instantly into our central kernel_main function. From there, the kernel initializes three critical subsystems. First, on the left, we have the GDT, or Global Descriptor Table. This establishes our core system rules and administrative access, which is a required step before we can unlock the specialized CPU hardware needed for fast math processing. Next, in the middle, we have the IDT, Interrupt Descriptor Table, and ISR, the Interrupt Service Routine, which handles our crash protection. And together they safely catch hardware errors and route incoming interrupts so the system remains stable and doesn't freeze. Finally, on the right, we have our memory management, which is handled in two specialized layers. The PMM, or Physical Memory Manager, maps out the raw RAM to track exactly what physical space is available. Above it, the VMM, or Virtual Memory Manager, acts as our data organizer. Crucially, the VMM is built to allocate massive 2 megabyte huge pages for our system. By organizing the memory into these large blocks, we drastically reduce system overhead, allowing us to process incredibly heavy mathematical workloads without slowing down at all.
The piece of the project that I'll be presenting is the network stack. So this will include the full pipeline that gets a math workload from a host machine into kernel memory and then ready to execute. So as you can see from this first chart here, at boot, the kernel calls the PCI scan bus, which loops over every bus, slot, and function on the motherboard using a port I/O to read each device's vendor and class code. The reason why we do a full brute force scan like this is that there's no OS here to hand us the device handle. We have to find the hardware ourselves. So then when when it finds a class 0x02, which is Ethernet controller, it wakes it. You can see that that wake sequence here. We walk the device's capability list to find the power management register, force the lowest 2 bits to 0 to push it from the D3 sleep mode into the D0 awake mode, and we wait 10 milliseconds for the hardware to stabilize. That step is crucial on real hardware. If we skip it, the card simply won't respond. Then we enable bus mastering and memory management I/O, and that gives the NIC permission to talk to the rest of the system. We grab the interrupt request line, and based on the vendor ID, we dispatch to the right driver. The driver maps its hardware registers and immediately wires itself into the network code via these 2 function pointer registers here. From that point on, the rest of the kernel never touches the hardware directly. It's completely abstracted away. Right now, I'll hand it over to Lucas, who will walk you through how these drivers actually work under the hood.
One portion of this system that we abstracted in the diagram explanation is the network interface card drivers. We decided to not cover them in depth because they are very hardware specific and are drop-in pieces in the system overall. So for this project, we wrote several sets of drivers for different use cases. We had one driver for a very old Intel network interface that we used for emulated runs of the operating system on QEMU. One driver for our demo day device, the Toughbook CF33, which runs the Model i219 network interface, and one driver prototype for our backup demo day device, an HP Victus, which we ended up not moving forward with as it was eating way too much development time. So the brunt of the implementation for these components was mainly reading datasheets for the specific hardware. You need to follow the instructions and flip the bits to successfully initialize with the different configurations you might need, as well as follow what the protocol should be for these interfaces.
Thanks, Lucas. So once the driver is live, there is a receive flow on the left. The host sends the first Ethernet frame carrying our custom Ethernet type 0x88B5. We used a reserved experimental ether type so that there's no other traffic on the network that accidentally gets interpreted as a workload. The NIC fires a hardware interrupt. The kernel checks the ether type and then parses out for our magic number and the payload size of the frame payload. Our magic number in this case, we've just gone to go, all caps, exclamation point, and then then we get the payload size. Those 2 pieces of information together are the handshake. The kernel now knows a real sender is on the other end and knows exactly how much memory to ask for. It goes to the VMM, the virtual memory manager. It allocates the right number of huge pages, 2 megabyte huge pages, and opens the data path. From that point, it's a loop. So every subsequent data frame triggers another interrupt, and its payload gets written directly onto the huge page. So there's no intermediate copies, there's no busy waiting. The CPU sleeps in between interrupts and wakes only to write. When the last byte lands, the kernel casts the memory address to a function pointer, and the workload executes. On the right is the return path, where the workload completes. The kernel builds an Ethernet type, writes a transfer descriptor, signals the NIC to DMA it onto the wire, and waits for the transfer complete interrupt confirming delivery. And that's the network layer. I'm going to pass it on to Ian, who will talk about the user journey.
So this is the user journey and what the experience actually ends up looking like end to end. If someone wants to use the OS, they'll need to install the VS Code extension. Then by opening their project folder, the SDK will auto-generate the header file, linker script, and makefile, all of it ready to go without any manual setup required. From there, they'll need to write their workload in C with full access to the kernel's math and memory APIs. Hitting compile would allow the user to produce the binary, and then hitting stream will allow them to send that binary directly over to the unikernel through Ethernet. The kernel will then receive it, execute it against the hardware, and then write the results to the frame buffer. With all these steps, users are now able to run their workloads directly on hardware with nothing more than a C file and a VS Code extension.
All right, so this slide covers our benchmark results comparing the Unikernel against Linux. For this, we ran 2 tests, a dot product and general matrix multiplication, and we tested Linux both at idle and under load. So starting with the dot product, all 3 basically tied at around 9 milliseconds, which is to be expected because it's a shorter memory bound operation that finishes fast enough to where Linux cannot, there's no OS interference because it's so fast. The difference can be shown in the general matrix multiplication. The Unikernel completes it in 1079 milliseconds, while Linux idle comes in at 1459 milliseconds, and Linux under load taking 1771 milliseconds. This is a 26% improvement over Linux at idle, and it is over 60% faster than Linux under load. The reason why this gap is more pronounced is because Linux has to handle context switching, handle interrupts, and run other background processes. Because the Unikernel is dedicated to this operation, an application, it runs straight through without giving any CPU to other processes. You can also see the difference in cycle counts. In the dot product, the Unikernel stays consistent at 26.4 million cycles, while Linux under load goes up to 34.6 million. Also on the general matrix multiplication, you can see 5,142 million cycles for the Linux under load, and for the Unikernel, it takes 3,135 million cycles. The key thing to note here is that the Unikernel is deterministic. It takes the same time to run the application every time. There is no variance because there's no operating system overhead getting in the way. These results will also be more pronounced as you start to scale workloads. Here are some of the challenges we faced and lessons we learned from this project. So for most of our computer science careers, operating systems have just been black boxes. We use them, we may study some system calls, but we never really get to see what's underneath. This project changed that. We stripped away every layer of abstraction down to assembly to understand how real systems are actually made. We built hardware drivers, paging, an interrupt descriptor table, and AVX and SSE support directly from datasheets. No operating system safety net to catch us. The hardest part wasn't any single component, it was system cohesion. Getting the bootloader, memory, networking, and workload execution to all slot together precisely was a real design challenge. Also, debugging bare metal systems with no standard tools forced us to develop techniques and skills that will transfer to working on any complex software environment. The result is, for us, is a much deeper operating system intuition, and that will directly improve how we write software at every level.
Finally, ending off with how future work of this project can look. Obviously, there's countless of ways that it can and hopefully will be pushed forward. Some of them being having more driver support, expanding either the math library or the networking protocol, enabling internet connection, having algorithmic optimization in core systems, or rewriting in other language, such as Rust, for example. But yeah, those are ways that we want to hopefully see this project move forward in the future.